hope you didn't forget too much. So yeah, you'll have to use this temporary this projection. So let me start with the following lemma. So suppose the topological space X is a union of open sets A alpha, labeled by some index alpha, and also let me fix some point x0 in X so that it also belongs to A alpha for any index alpha. And we also want to assume that alpha are all path connected. And we also want to assume that moreover intersection of any pair of alpha of two open sets A alpha and beta for any pair alpha and beta is also path connected. Then, given these conditions, we want to show that for any loop f, that is any loop f in X that is a map from unit interval to X with a base point equal to my chosen point x0. Here there exist loops hi inside some open sets A alpha. So suppose index I runs from 1 to n such that f is path homotopic to a composition of these loops h1 and hn. So of course, so we understand here the loops are understood as loops in sets, but of course since any set can be included in X, we can understand those loops as loops in X itself. So we can compose them as loops in X, and the statement that this composition is in X. So is it readable like this?
Is it always necessary that these loops are finite in number?
Yes. This is we want them to be a finite number. So let us prove this. So first of all, so f is continuous by definition of a path. Then for any s inside the unit interval, there exists an open interval, let's say Vs. So we can assume that without also generalize that this the closure of this open interval is some closed interval, of course, and so in principle the continuity tells us that the interval the continuity tells us that we can choose such interval so that the image of Vs belongs to some particular A alpha here. But we also, without also generalize, we can also assume that actually the image of the closure of this interval, just by taking a little bit smaller interval, the closure of this interval belongs to a certain, we can always choose these intervals such that they belong to a certain open set A alpha by definition of the continuity. And then, of course, this the unit interval is given by the union of these open intervals, and from the compactness we can choose finite cover. Finite subcover, so there is a finite number of intervals, of closed intervals, which cover the whole unit interval. And those intervals will satisfy the condition that the image on the F belongs to, lies in a particular, in some open set A alpha, which covers the whole space X. And so using the argument which we used before, it's easy. From this, it also follows there exists a partition of unit interval that is a choice of finite choice of points which start from 0, which we will denote by S0, S1, S2, and so on till Sn, which we will identify with 1, such that for any I, the image of each small interval between neighbor SI's belongs to some open set A alpha. So why from this compactness, why this prediction exists? For example, we can choose SI's to be all boundaries of VS's. Here by VS's, the open intervals, I mean the finite number of VS's which we choose to cover this guys. So we can choose all these boundaries, you can order them like here. And then we will have this division of unit intervals, so that each into small segments, so that for each small segment satisfies this condition. Okay. So now we want to use another condition of the lemma in the formulation of the lemma. So since for any pair of open sets A alpha, the intersection is path connected by the formulation of the lemma. So in particular, for this for a pair of open sets with index A alpha I and alpha I plus 1 is should be path connected. And therefore, in particular, it follows, so since each of these guys contains point x0, it follows that there exists a path for any I, index I, there exists a path gi from x0 to, let's see, to fsi, such that so the image, so this path, so the image of this function gi lies in this intersection. So it lies both in A alpha and A alpha I and A alpha I plus 1. So also so let me denote by f with index I to be the part of path fi, sorry, part of path f from f of si to f of s, sorry, from f of si minus 1 to f of si. So more explicitly, I can choose. So if I understand this path as a map from a unit interval, so I can choose the explicit parameterization as follows. So this will be given the function from the from the unit interval will be given as follows. Right. So when s is 0, this is equal to fsi minus 1, and when s equals 1, this equals to fsi. So let me draw a picture. So what is a picture of this kind of construction? So we have some space X, we have a path, some path F inside. So this is S parameterize the path, so S goes from 0 to 1. So we choose a division of the unit interval. So this will be a point corresponding to image of 0. This will be point which is the same as 0. This will be image of S2, S3, and so on up to Sn minus 1. And so here, so this path which goes from here to here, I will know by f1. This small path from this point to this point, I will know by f2. So to be more precise, since we are drawing this picture in X, so this is the image of S1, this is the image of S2, and this is the image of 3. And then, so we chose, so what about this GIs? So this is a path from x0 to fsi. So for each of these points, we chose a path from x0 to this point. So this will be g1, this will be g2, this will be g3, and so on. Then, so from this kind of schematic picture, so of course, so since f, so we split, so by construction, f is a composition of paths f1, f2, and so on up to fn. But of course, we can, so up to homotopy, we can insert. So first, after f1, we can insert a path which is inverse to g1 together with g1 itself. And then after f2, we can insert a path which is inverse of g2, and then g2, and then we go along g2 back, and then f3. And so on up to, so let's see what at the end we'll have g n minus 1 times this will be fn. Okay. So we represented f as a up to homotopy as a composition, as a following composition of paths. So essentially, we go like this, then we'll go like this, then we'll go like this, and so on. And then we so let me rearrange the pass as follows. So F1, first we write F1 composed with G1 inverse, then G1 with F2, G2 inverse, then G2 times F3, G3 inverse, up to Gn up to Gn minus 1 Fn. So we have now we want let me denote this pass by H1, this pass in the parentheses H2, this H3, and so on. The last will be Hn. And then by construction, which we had before, one can see that those paths they lie completely. So I's path lies in A alpha I. So this is because first of all, Fi lies in. So this follows from. So we chose Fi such that the image of path Fi lies in alpha I, and moreover, we chose that both Gi minus 1 and Gi they lie in also A alpha. Yeah, just A alpha. This is because each Gi lies in the intersection, right? So in particular, it lies both in this and this guy. So since, so for example, here each of these guys lies in A alpha 3, so we did have this condition. And so so this is essentially concludes the proof of the proposition. So we represented path F as a composition of passes HI's which satisfy this condition, which is what we need. Any questions? So let me illustrate how one can use this lemma. So let me show the following corollary. So the fundamental group of Sn of n-dimensional sphere is trivial when n is greater than 1. So before we used, we proved that pi1 of S1 is isomorphic to Z. Here we want to show that for high-dimensional spheres, the fundamental group is trivial. So how does this follow from the lemma? So first of all, we want to choose a particular representation of a five-dimensional sphere. So the most standard one, so we represent it as some subspace in n plus 1 dimensional Euclidean space. Given by the following equation, so the sum of squares of all coordinates is 1. So now we want to choose. So we want to choose some cover of Sn by open sets to use the lemma. So in this case, we will need just two open sets, A1 and A2, and in particular, we take A1 to be a sphere with just one point removed. So we remove a point with coordinates 1, 0, 0, 0, and A2 is a sphere with minus 1, 0, 0, 0. Point removed. So if So one can visualize this as follows. So I mean, this is so for example, for n equals 2, our sphere looks something like this, and the one of the points which we remove is the north pole, and the other is the south pole. And A1 is a complement of this point of the north pole, and A2 is a complement of the south pole. So of course, it's easy to see that the intersection is path connected. So here, for this condition, here this is important that n is greater than 1. When n is not, so for example for n equals 1, the sphere would be like this, and if you remove poles, this A1 and A2 wouldn't be the intersection wouldn't be path connected, so just two disconnected guys. So now it's so what is the fundamental groups of the individual guys? So one can show that these fundamental groups are trivial. So why is that? This is because for each AI, it's homomorphic to Rn. One can see this, for example, using stereographic projection. So, for example, how do we, in this example, when n equals 2, how do we explicitly contract homomorphism between this A1, which is a sphere with removed north pole, to a two-dimensional plane. So we draw a two-dimensional plane which touches the sphere at the south pole, and we map the point by projecting it to a plane along the line. So this point maps. And since the fundamental group of higher Rn is trivial, it follows that pi 1 of Ri is trivial. So in particular, all cycles, all loops in AI are contractible. And therefore, so from the lemma, it follows that phi 1 of Sn should be also trivial. So since any loop in Sn we can present as a composition of loops in IIs, it follows that any loop in Sn itself is also conductive. Questions? Okay, now so we'll need to introduce some definition in order to press it forward. So if you want to define the notion of, so maybe you're already familiar with this, but anyway, so we want to define a notion of free product of groups. So suppose we have groups H alpha labeled by some index alpha which belongs to some set I. So the free product is a group, be new group G. So it's denoted by, so the free product is denoted by star. For example, if there are just two groups, H1, H2, so G is, so we write it like this, H1 star H2. But if there are multiple, so you can write with notation like this. So how is G defined? So first we want to define it as a set. So as I said, G is, contains all possible so-called words or formal products of elements. So this is essentially a sequence of elements G1 from G1 to Gn, such that Gi is an element of group H alpha I. So if you have an element of some of certain group H alpha, and more we want all elements. So the neighbor elements here to belong to different groups H alpha. That is, if the indices differ by 1, then alpha I is not the same as alpha G. So again, we write, so the elements of G are sequences of elements, formal sequences of elements of the groups H alpha, so that the neighbor elements belong to different groups H alpha. So now we want to define what it is as a group. So we want to define multiplication. So how do we multiply such two words? So let's say you have a word G1 Gn, and then we have a word G1 to G1 prime, and nth is G prime M prime. So we want essentially we want to say that this so we want to obtain some new word, some new sequence of elements. And we want to say that this sequence of elements just is basically we concatenate these two sequences. But in principle, this this new word may not satisfy this condition, because, for example, those two guys, it may happen that they belong to the same H alpha, to the same group in this family. So we want to say first that we want to reduce this word according to the following group. So if in the word we have we encounter two neighbors such that they belong to the same H alpha, we want to replace it by, so in this place we want to replace this by an element which is a multiplication of these two elements in the group H alpha. So we may use so in order to obtain a word satisfying this property, we may need to use this a few times, but we always it's easy to see that we always require finding number of such rules, to application of such rules. And it's easy to see that this multiplication satisfies group axioms. So I'm not going to show it in very detail. So in basically it satisfies associativity, existence of inverse. So so let me show, for example, so the unity here is just a trivial word, or we can so word with 0. So this m here can be 0. And for example, if you want to construct the inverse, you have a word and we want to construct its inverse, is given by taking the word in the opposite direction and taking inverses of the set. It's easy to see that according to the multiplication, if you multiply this guy to this guy inside the brackets, we'll arrive to a trivial word after doing this simplification, after applying this rules like this. And the third is assertion, which I'm not going to show. This is lecture exercise. Again, intuitively, it's kind of clear that this is assertion. Questions about the definition of the free product?
What is n prime? Definition of multiplication.
Here, n prime. So we choose. So elements of G are some words of finite length. By word, I mean just a sequence of elements of groups, a certain sequence, so that each element of a sequence is the element of a certain group H alpha. So here we combine, this means that we multiply words of a different lengths. So here the length is m, and here the length is m prime. By length I mean the number of elements. So let me give you an example. Let's see. So suppose you want to consider a free product of group Z2 and Z2. So this Z2 you can realize, of course, is just the group Z2 can be realized. So it just contains two elements, one and A, such that A squared is 1. And this contains two elements, A, say 1 and B, such that B squared is 1, right? So two group Z2s, cyclic groups of order 2. And then G are sequences of the form, the words of the form A, B, A, B, A. So we cannot B and so on. Or B, A, B, A. And for example, if you want to multiply A, B, A with say itself, this is equals to 1. So first we apply the rule, A squared is 1, we remove it, and then apply rule B squared is 1. So the free product of groups has the following important property. So suppose you have homomorphisms phi alpha. So homomorphism from each component of the free product to some group K. Then we can define a free product of these homomorphisms, which we will also denote as a star by star. And this will be a homomorphism from a free product of groups H alpha to K, such that an element here given by some word, each letter of this word is an element of some H alpha, is so it's mapped to let's see. So suppose this belongs to suppose this belongs to H alpha 1 and this belongs to H alpha m. So this goes. So we take a product of. So we essentially apply it for each element of the word here. We apply a corresponding homomorphism. So for G1 we apply T alpha 1, and so on. And for the last we apply T alpha m of Gm. And we just multiply them as an elements in group key. And again, it's easy to see that this is indeed a homomorphism. So if you multiply words here, it's clear that we multiply elements here. So this is a homomorphism. So let me, also for simplicity, let me introduce the following notation. So let me assume the conditions of the last lemma. So remember that there was a topological space, which was a union of open sets A alpha, which satisfies some nice conditions. So they were all path connected, they all contain some fixed base point. And more or less they were pairwise path connected. And so let me denote by I alpha the inclusion map from A alpha to X, and by I alpha beta the inclusion map from the intersection of two open sets into the first one. And so if you remember, for any map, any continuous map induces a corresponding map between fundamental group, which we call push forward. And the corresponding push forward for those guys I will denote by J alphas. This should be useful. This is J alpha is a push forward of I alpha. That is, it will be a map from pi1 A alpha with base point x0 to pi1 of the total space x with the same base point. And similarly by J alpha beta, so this is, I will denote the push forward of I alpha beta. This is the map from pi1 of intersection to pi1 A alpha. Okay, so we introduce the following notations. So now we can formulate the one content theorem. So again, let X be a union of open sets E alpha, so that each contains a base point 0. So they satisfy the same conditions as in lemma. this both A alpha and the intersection for any alpha beta are path connected. Then the first statement, so the theorem has two statements. So the first statement is that if you define a map phi by star product of maps G alpha is here, so this will be, so by definition, the star product of this free product of homomorphisms, the homomorphism for my free products of pi 1s of A alphas to pi 1 of X. So this is a free product of maps here. And the statement that this is this map is surjective. And the second part, so we want to more assume that if for any triple, not just any pair, but for any triple of open sets A alpha, A beta, A gamma, their intersection is path connected. For any alpha, beta, gamma, then the kernel of map phi is equal to M, which is a normal subgroup of so phi maps from this group, so this will be normal subgroup of free product of pi 1s of A alphas generated by elements of the following form: J alpha beta omega times J beta alpha omega inverse, where omega is some element of pi 1 E alpha intersection, E beta is base point. So let me remind you that J's, so they define like this, so they map so from pi 1 of the intersection to pi 1 of a single of the first guy of the intersection. And moreover, of course, each element here can be included in the free product. In other words, so the kernel, if we identify the kernel of phi by n, so we mean that pi 1 of x is homeomorphic to the free product of this guy's quotient by n. And this is just follows from the definition of the kernel of the map phi from this group to the group. So essentially, this the statement of the theorem allows, so explicitly allows a way. So if you have this particular nice cover of space X, it allows to explicitly determine the fundamental group by knowing the fundamental groups of these open sets covering space X. So it's so the first part is essentially the reformulation of the lemma. So because the statement this is surjective means that any element here can be represented by a product of elements here, which is order property. So this proves that this map is surjective. So the proof that this is injective will require some work. It's much less clear. So any quick questions about the formulation of the first part? Okay, so before we proceed to the proof, so again, we need to introduce some notions. So let us call formal product F1, F2, and so on to let's say Fn, where each factor here is an element of pi1 A alpha I is being put at 0, so Fi is a certain path representing this element. So this is a path inside some more words. It's not just a path, a loop inside alpha I, which of course can also be understood as a loop in the space X, which contains space A alpha I. So we call this product a factorization of element F of pi1 of X if F is homotopic to a composition of paths from F1 to Fn. So it always exists from the lemma. Right. But what we want to do, we want to consider a certain equivalence relation on such factorizations. First equivalence relation, so suppose we have a factorization of the following form. So we have some elements, then we have Fi and Fi, then Fi plus 1, and then something else, so that this guy is, so that both of these guys, they actually element of pi1 of the same A alpha for some index alpha. And then we want to say that this is equivalent to just replacing this pair of elements by an element corresponding to composition of the corresponding paths. the second equivalence relation. So suppose we have Fi somewhere in the middle, and let's say this. So this is can be understood as the element of A alpha, but suppose the path Fi is such that it lies entirely in the intersection of A alpha with some A beta. This means we can also understand this path. So the path inside A beta, and therefore we can understand this element as actually an element of a different group, of a group pi 1 A beta. So it's the same path, but it can be understood as a representative of an element of a different group. Here it's pi 1 of A alpha, and here it's pi 1 A beta. This is we can do this whenever the path lies in both of them simultaneously. So we can also understand this equivalence relation as follows. So, so we can also understand since Fi lies in both of them, we can also understand Fi, let's say, let's denote it by, to distinguish from these guys, let me denote by omega, as the omega which is the element from pi 1 of the intersection. And then, so this element can be understood as J as a push forward of this guy with respect to inclusion mark from the intersection to A alpha. This should be J alpha beta of omega. And this guy similarly can be understood as a J beta alpha of omega. But of course, we can also rewrite this guy as follows. Just say combine J alpha beta of omega times J beta alpha of omega inverse times G beta alpha of omega. So presented this element as the same element as here times something here. And we see from the definition of the normal group and above in the formulation, this is the element of my normal group N, right? This is the definition of N above. So I remind you that so N is the normal subgroup of this guy generated by elements of this group. So therefore, if one understands this kind of these factorizations as the formal products, as one can say some kind of unreduced words of elements of this group pi 1 of A alpha. So this equivalence relation essentially tells us that we reduce a word. So we want to avoid this the situation when the two neighbor elements are from the same group. And here we want to quotient with respect to elements of this normal of this subgroup N generated by the elements of this form. So this means that the equivalent, one can say that equivalent factorization give the same element in say group Q, which we define as a free product of pi 1s of A alphas divided by the normal subgroup. So again, this is so this equivalence relation brings. So once we apply this, we arrive to some unreducible word, which is convinced of the element of this free product. And this equivalence relation means we factor. We want a quotient with respect to all elements. And so the statement of the theorem is that so we want to show that in order to prove the second part of the theorem, we want to show that any two factorizations are equivalent. That is so the map induced by the map phi, so from the map from the free product of groups pi 1 of alpha quotient over normal subgroup M to pi 1 X is injected. Or equivalently, the kernel phi is if we mean, so this essentially tells us that if we have two different representations, if they give the same element in pi 1, then they differ by they differ by element of M. So the kernel phi is the same as M. Questions?
Why we need intersection of A alpha with A and also A gamma is cross connected?
Well, we will need it in the proof. We will need that. I mean, for the intersection, the pairwise intersection, we already need it in lambda, right?
Yeah.
So to show this part, the part that is the phi is surjective. So any element here can be realized as an element of here. But we will need this when we're going to prove for this 2. So we haven't proved yet 2. We just show that we want to show that if we will prove 2 if we show that any two factorizations of plus and x are equivalent. We want to show this. In the proof of this, we will need this condition that any triple, the intersection of any triple will be plus connected. Is this the question? Any other question? So we want to, okay, now we want to show that if we take two different factorizations of a path in X, they are different by these equivalence relations. So they differ essentially by just some trivial operation, which is a multiplication, and by changing them by an element of M. So let me take one factorization to be F1, F2, and so on, FL, and the other factorization will be F1 prime up to F cube. So by definition of the factorization, there exists the factorization is such that the composition of this past is homotopic to F. So this means there exists a homotopy F. It's a path homotopy. Path homotopy F that is the map from a product of two intervals to X from composition of paths F1 till FL to F1 prime FK. So now I want to use an argument similar to the one before. So F is a continuous map from the square to X, and X is a covered by open sets A alpha. This means that we so again we want to use. So similarly as we used the compactness of the interval in the lemma, we want to use the compactness of this product of the interval. To show that there is a there exists a finite cover. So finite cover of the square by rectangles, let's say AB is for CD, such that the image of each rectangle under the continuous map F is contained in A alpha for some alpha. So again, this follows from continuity of function F and the fact that the square here is a compact. Okay. And again, from this, also similar to as in lemma, there exist partitions now of both intervals. So first there will be partition of the first interval by as so there will be a finite number of points as 0, as ordered points as 0, as 1, as 2, and so on till Sn, which is the same as 1, and also partition of the second interval, T0, T1, and so on till Tn plus 1, such that for each, so this gives, so for each rectangle which is given by product of small intervals between neighbor points here, for each rectangle of this form, this belongs to some A alpha, let's say A alpha ij is in this ij. Sorry, I mean here, big, of course. F is a function from. So again, so this can be shown similarly as now. So let me in bit elaborate how we go from this kind of covering by rectangles to this kind of partitions of two intervals. So this, so suppose we have some square. This will be so let's say this will be a partition. Yeah, this will be direction S, and this will be direction T. So this is the direction of parameterization of the path, and this is the T, the homotopy parameter. So suppose you have some sort of color of the big rectangle by small rectangles like this. Right. And then what we do, so we have a covering of rectangles by rectangles of the big rectangle, so that each rectangle maps to some alpha. Now we want to create this, these two partitions. We essentially want to continue all edges. So we obtain the following grid, and so we obtain rectangle grids. So this will be S1, this will be S2, S3, S4, this will be T1, T2, T3, T4. So the cover by this kind of small rectangles of this form will be subcover of these original rectangles. So of course, if this condition was satisfied, this condition will also be satisfied. So we write with the following kind of grid subdivision of rectangle by small rectangles. So that each rectangle, what's important here is each rectangle is mapped, the image of this each rectangle under map F is contained in a certain, completely contained in a certain open set A alpha. Now what actually we want to do, so this is not very good for a proof, so we want to do a small deformation of this small perturbation. So, small perturbation. Such that each vertex meets at most 3 edges. So here, for example, this vertex, it meets 4 edges. What we want to do, we want to shift a little bit. We can do this without kind of spoiling this condition. We can shift a little bit each edge here, 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 here in the horizontal direction, so that you obtain a grid kind of the following form. So we'll have horizontal lines. So we will have some division here, and then the above these vertical lines will be a little bit shifted. All right. So now, each vertex here it meets at most 3 edges, not 4 like here. And so here it's yeah, the picture is not good, but this yeah, it's important that this guy is separated a little bit. Now we want, so for convenience, let us relabel rectangles, small rectangles, by R1, R2, R3, and so on till. So we have in total n times n rectangles. So that they are ordered like this. So here will be R1, R2, R3, R4. So in this example R5, and then we go here R6, R7, R8, and so on till here you'll have R. And of course, when we do the small perturbation, we will still we can preserve the condition that the image of each rectangle Ri here is contained in a certain open set A alpha line. So we can do this. So we can go from this picture where this was satisfied to this picture with a bit shifted line. It's infinitesimally shifted edges. So this is we still have this condition. Now instead of the double index, we just use a single index, which will label the guys like this in this order. And now we want also, let's say, let us take path. Let gamma r be a path in the square that separates rectangles R1 till RR from the est. So let me give you an example. So for example, if I want to write gamma 6 here, it will go like this. Right? So it will separate R1, R2, R3, R5, R6 from the rest. So in particular, so this is, for example, the gamma 0, the path gamma 0 will be like this, and the path gamma mn will be like this. Is it clear how the path? So the gamma r is a path in this rectangle. How is it defined? So of course, so we know that so f was a path. So f is a path from is a map from this rectangle to x. And so since the path homotopy, this h, this h is mapped to, and all this h is a map to the same point, x0, to the base point. So this is the whole this thing is mapped to x0, the leftmost, the left edge of the vector, and the same thing. To the right edge. And so f is path homotopy in x. So it follows that if you consider composition of f with gamma r, this will be a loop. Sorry. Is a loop in x, because the endpoint. So since so if you take the composition at 0, this will be the same as the composition at 1. Because the beginning of each gamma r lies on the left edge, and the end of each gamma r lies on the right edge. So each such composition will be a loop in x. Yeah, let me write this. Let me draw this figure again. clarify here, I will exaggerate a little bit the kind of the shift I do, so it's more clear. So now I want to consider vertices. So vertices in this kind of grid here. So each, since we did this perturbation, so each vertex V is adjacent to at most three different rectangles. Let's say R I1, R2, R3. Right? So now this is rectangles in this case, and so since it follows that, so now I remember that the image of RI it belongs to a alpha I, and so we want to use the condition of the theorem that the intersection of any triple is path connected. In particular, the triple corresponding to those three guys, to this triple of rectangles, is path connected. Therefore, there exists a path which we will denote GV in this, which belongs to this intersection. But of course, this can also be considered as a path inside the space X, because this belongs to X. There is a path from X0 to F of V. So we use the fact that this is path connected, and moreover, is this, of course, since any of them contains X0, this contains X0. And F of V, since we have this condition, in particular, F for the image of this vertex belongs to all three guys. Since the intersection of these three guys is path connected, there exists a path which we call GV, which connects Z0 to image of this vertex. So this is a place where it's important. It's important to have this condition with the triple is
if f of v is equal to x0,
f of v is equal to x.
x0,
Well, then this is a trivial path. Yeah, just constant. For example, if v belongs to any of these vertices, you can just choose a trivial constant path. And here, so since you can also see we needed this perturbation. So otherwise, if you didn't do this perturbation, there will be four different rectangles meeting at each vertex, and you will need a stronger condition. So So you need this perturbation to have just this condition for triples. Any other questions?
Also, one question. What condition may us to perturbation such that the one each contains as three?
Well, we need, we want, so we use the fact that f is continuous function. And essentially we use the fact that not just, we can use this kind of the original rectangles, we can use not just this condition satisfied, but actually there exists a neighborhood. We can choose such as there exists a neighborhood of this rectangle containing A alpha. That's why if we a little bit kind of widen the edges, we will still be in the neighborhood, and it will still belong to A alpha. And we can use this condition by just like taking some, taking this kind of some subcover and then reducing. We can always use this kind of name smaller squares.
So finite cover is opposite, and we choose closest, so we can.
Yeah, we choose these kind of. Well, we can choose a finite. So we can choose the cover by. So first of all, we choose a kind of. We choose the cover by rectangles, by kind of open rectangles, so that the image contained in A alpha together with some neighborhood. And then we choose those intervals with the closure of this, those kind of rectangles with the closure of open rectangles. But of course, they also will be contained in the neighborhood. So this neighborhood is also mapped to a certain A alpha. That's why if you perturb them a little bit, they will still be inside the A alpha. Okay, so we are kind of close to drawing this here, but not yet. So let's see. So okay. So we chose this. So for each v, we chose a path gv from x0 to the image of v under f. So then, for each path gamma r defined as before, there is a factorization of composition of f with gamma r. Given as in lemma. So what is it? Let me elaborate on this. So before the path, so as I was here, for example, the path gamma looks something like this. So it's a path, some path inside the rectangle, inside a big rectangle from left edge to the right edge. And then, of course, so it will meet, so let's look something like this. So it will meet, there will be some vertices of this grid along the path. And And so let me number V1, V2, V3, so on. And let me also denote. So as a lemma, I want to split path gamma r into small paths. So gamma r1, gamma r2, and so on. And then, so what I actually want to be, so we want to consider factorization of composition of gamma r with f, which should be a path, as we showed before. This is a path in X. So what we want to do, we want to first split it into gamma r into small paths, gamma r1, 2, and so on. And then we want at each, in each between them to insert, again as in lemma, the passes which go from x0 to the value of the pass at this point. So the value of this point is f of v. And for here, for this we will use this orthohomotopy, of course. So we want to do the following split. So first, this will be path which goes from the x0 to f of v1, and here we had the inverse of gv1. So this will be a path which goes from f of v1 to x0. And then we add a path which goes from x0 to f of v1, and then we add the composition of f with gamma r 2. And then we use a path, the inverse of path gv2. So the path which goes from f of v2 to x0. So to be okay, let me just finish the thought here. So how does it, so let me, so for each, so so to be more concrete, so for each interval I have the following situation. So I have some interval, say between I1, I, and this will be gamma r I, and so I will have some. So for each edge, I will associate. So for an edge like this, I will associate GI minus 1 composition with f gamma I GI. And so suppose this h, so at one side of this h there is a square RA, and for the other side there is a square RB. And then, so using the properties of this path, of these rectangles and paths, we can see that this is, so if we, this can be interpreted as an element of phi1 of A alpha A, or an element of phi1 of A alpha B. So this is because, so if we, in the first case we use the fact that the whole rectangle is mapped to A alpha I, and the vertices, the passes GV I minus 1 and GVI, they also belong to this subspace A alpha I. Okay, so my time is over, so I'll have to continue next time. Any questions?